What's going on, guys? Welcome back to this video. Today's video will be again on HackTheBox platform, and we're doing Optimistic, which is the third challenge in Intro to Binary Exploitation track. Again, Intro to Binary Exploitation track is a beginner track that teaches you how to exploit buffer overflow vulnerabilities. Right, so let's get to it. So we click on Optimistic, and here we start the instance because this is a remote binary. So in order to exploit the binary, we're gonna have to connect to the instance hosting the binary on the given IP and the port. Don't forget to download the files as well. So here I go to my virtual machines, and I'm gonna launch a new terminal session. And from here, we're going to examine the binary. CD desktop. And here we're going to say file optimistic. Let's take a look here. So it is 64-bit executable file, and it is not stripped. Remember, guys, what I told you about stripped and non-stripped binaries. So basically, stripped binaries make it harder to reverse engineer the file and reveal the main function and other symbols. So since it is not stripped, our life now gets a little bit easier. So the next thing, we want to examine the source code of the file. So we're going to go to Gitra and run Gitra here. So we want to take a look at the source code, how the binary works, what are the different functions, the variables, the buffers allocated to these variables. And we want to look if there is a buffer overflow vulnerability in this file. Let's take a look at what type of buffer overflow vulnerability in this file. So I have already a project here. I'm gonna right click, so I'm gonna go ahead and click the open. Let's import the file. The session file name already exists. Okay, so let's take a look now at the main function. So we have a couple of variable declarations here, and then we have, as you can see, the welcome screen. It asks you for would you like to enroll yourself, and you're gonna provide with yes or no. As you can see here, the input of the user is taken to this variable local underscore 7a, which is here. Now if you type yes, if you don't type yes, if you type no, the code would execute the if statement here and will tell you, too bad, see you next time, and assigns this number, this byte, as you can see, 110 bytes to local 78. Local 78 is defined here. Okay, let's follow on with the execution flow. Right, so if you don't type no, rather you typed yes, it's gonna resume the execution and go to this statement. Great, here's a small welcome gift, and here it leaks a memory address. Let's take a look at this memory address. So it is let's see here. So we have this one, local 88. As you can see, most of the variables that are defined are well mentioned here. So we have local 84, local 80, 7C, 7A, 79, and this is the leaked memory address, which is here. So this address will be used in the exploitation phase, because it's a leaked memory address that points to the base pointer here, right? And then move to the stack pointer, as you can see here. So what we have to do, we have to take a note of this memory address, because later we will be using it in the exploitation phase. And then we're asked to provide details. Please provide your details. Here it expects you to enter an email address. The email address should be, as you can see, 8 bytes. With the read function, we read an input from the user, and we expect 8 bytes to be entered by the user and will be stored in the AUStack78 variable, which is defined and declared as being 8 bytes. So it's 8 bytes, the buffer is 8 bytes, and the user should enter 8 bytes. If you enter more, you're not going to achieve overflow, by the way, because it is defined how many bytes we should enter. So it's going to not work. And then we have printing age. The age is again 8 bytes. It has to be 8 bytes and it is stored in AUStack70, which is again 8 bytes. And then we have printf. It asks the user to enter the length of the name. Now the length of the name, as you can see, is taken using scanf. And the length of the name will be stored in the local 84 variable. The local 84 is defined here. Local 84, as you can see, guys, if you go to the assembly view here, local 84 has 84 bytes in hex. So if you scroll down, another thing to note about local 84, it is unsigned integer. So when you see an unsigned integer and that same integer is used in an input process, and then later down the road, we can see here, guys, that whatever you enter as an integer into local 84, it's gonna get compared to 40 in hex. So 40 bytes in hex, it is more than, it's 64 in bytes. So if you entered more than 64 bytes, trying to, in an attempt, maybe we attempt to overflow, right? So we enter more than 64 bytes, it's gonna compare. If it is less than, if it's more than 64 in bytes, it's gonna tell you, oh, there, you shouldn't be optimistic. Now, if you entered less than 64, so what's gonna happen here? It's gonna resume the execution and allows you to print your name. So one might wonder, how can we overflow the local 84, right? Because there is no check on the user inputs. In the previous functions, we saw that the read function expects 8 bytes from the user. Now here we use scanf, but we don't specify a threshold or a limit from the user input. So this would kind of give you a hint that you have to maybe, or you may try to overflow the variable. But look, here we have a check, a user input check. Now, what happens is what happens here is that the overflow is not connected or related to the size. It is related to the fact that the local 84, the input, is actually declared as unsigned integer. And here later on, it was casted to ulong. So if you enter anything, it will be casted to ulong and interpreted as hexadecimal. So to overflow unsigned integers, you might try to enter a value that corresponds to a maximum value in hexadecimal. So the maximum value is -1. So if you enter here -1, it will be interpreted here as 255 later on with ulong. So -1, as you can see, guys, it is less than 64 in bytes. Okay, it is of course less, so it's not going to enter this if statement. It's going to allow you to enter the name. And here, what happened, once ulong, or once the -1 that you entered is casted to ulong, it will be interpreted in hexadecimal, meaning it will be corresponding to 255. Local 68, this variable is here, it is 96 bytes. So 255 is more than 96, and you will have caused a segmentation fault. So that's it. So the overflow actually happens or relies on two pillars. The first pillar is that we have an unsigned integer casted to ulong, and then we have a variable, local 68, which is only 96 in bytes. So -1 in hex, it is 255, which is more than 96. So we also overflow the local 68 variable. And we have is alphanumeric here. So it also must be alphanumeric. So when you create the shellcode, you have to make sure that the shellcode is also in alphanumeric characters. Anyway, so what is the exploitation methodology now? The exploitation methodology now will rely on two aspects. First, we have to go through the user input process. We're going to say, yes, we're going to provide an email that's 8 in bytes. We're going to provide an age that is not more than 8 in bytes. And when it comes to the length of the name here, we know that whatever we enter will go through the local, will go into the local 84. So we're going to enter -1 to cause an integer overflow. If you want to research integer overflow, you can research it on Google. Integer overflow. Again, it happens when the variable that receives the user input is declared as unsigned and then casted to ulong. So if you enter the maximum value to cause the overflow is -1. So -1 will get us here and we'll print the name. The name is read into the local 68 variable, which is 96 in bytes. So given that we enter -1 here, will be casted to ulong, which will be 255. 255 is more than 68. Now you have a segmentation fault. Alright, so after causing a segmentation fault, you know, the gist of our buffer overflow is to go to segmentation fault and find the offset, meaning how many bytes we need after 96 to reach the return address, which is here. So finding out how many bytes needed to reach the return address will define or will pave the road to creating the exploitation methodology. So let's go to the notes here and check the BOF. And here also I noted down the cause of integer overflow vulnerabilities, as you can see here. So -1 will correspond to this hexadecimal value when it is casted to ulong. Okay, now let's now check the binary for the protections. So we're gonna launch, we're gonna CTDebug, and we're gonna say GTP launch the binary with GTP because we want to debug the binary. The first thing is check sec. Okay, so we have portable, we have by enabled. Okay, so which means the memory addresses are randomized every time the application loads. Fine, but we have NX disabled, which means the stack is executable. So which means we can create a shellcode and execute in the stack. Now let's go through the process of running the binary. So the first thing, we're gonna run the binary without GTP. So optimistic. Would you like to enroll yourself? Yes. Provide an email. So let's say 4 bytes test. Age 5 bytes. Length of name. Now for the length of name, we're gonna have to enter -1. Thank you. We will be in touch soon. So we're gonna have to execute again because for some reason it doesn't resume to the spot we want. So -1. Yeah. So here is the name. Now the name, again guys, remember that the name is 96 in bytes. Okay. So now after we bypassed the if statement here, we are able to overflow the name. So to overflow the name, we're gonna have to generate a pattern that's more than 60 bytes. So pattern create, we're gonna generate one more byte, 97. We're gonna take this pattern and feed it to the name. Assumingly, we should cause segmentation fault. So paste. That is an invalid name. Let's try one more time. Sorry, that's an invalid name. Alright, so let's generate another pattern. Yeah, the application is kind of buggy, so we're gonna have to try more than one time to reach, yeah, the stage that we want. And we're getting invalid name because it's of some characters. And don't forget that it is checking here on the name, and it must be alphanumeric. So we're gonna have to go back and modify the payload. So we're gonna use Python to generate a pattern of only A's. So Python -c, yeah. So we printed only 97 A's. One more character to cause an overflow. Yes, test 5 - 1. We're gonna enter now the 97 A's, and no segmentation fault happened. 5 - 1. Let's enter one more character. Thank you, we will be in touch soon. Let's go back to the code and see why the segmentation fault is not happening. So we are taking the -1 here. So it's actually going through this while loop. That's why it's not working. Yes, I got this to work after trying like for more than one time. So this one is, let's generate like 98. And yes, no segmentation fault. All right, let's do way more than the buffer can actually comprehend. So we're gonna go back. Yes, test 4 - 1, and then this is the name. And yeah, we code segmentation fault. All right, so let's do that in GDB. So here, let's create a pattern of 500 characters. Well, let's use the same pattern, you know, that one. All right, so take this here. All right, so now we're going to say run. Yes, test, and then we put 5 or 4 - 1, and for some reason it is exiting. Right, so we're not entering the stage of, we're not going through the stage of entering the name here. So after we have provided the length of the name, the app is exiting immediately here. So it's not actually asking us to print the name. It is taking the input, which is the length of the name. It jumps immediately to the while loop, and it is entering thank you, we'll be in touch soon, and then it is exiting. So for some reason the code is not working correctly when we open it with GTP. So for that reason, to find the offset after causing segmentation fault, we're gonna have to rely on pawn tools, okay, with some Python. So we're gonna exit GDB here, gonna clear or keep it ls. So let's find the offset. So we're gonna have to just write a bit of Python. So resources, yeah, let's take this. I'm gonna explain. So nano offset py. Okay, so first we import pawn tools, okay, and we import OS. So what happens here, we have an argument, we have a function that does execute the binary, okay. So if we don't provide here an IB and port, it's going to execute the binary from the same current working directory, okay. So which is what we want. So here we're going to change this to binary name, which happens to be optimistic. And now here we handle the user input. Remember, when we exploit buffer overflows, we're going to have to take the user input phase, or this input process that application expects into consideration when we want to create the exploitation code. So we have to integrate the user input process into whatever code you want to write to exploit the entire binary or some part of the binary. So here we start the process, we send the line yes to indicate that we want to enter the stage, and then we send 2 A's for the email, 2 A's for the age, we send -1, and then here we send the pattern, okay, that goes into the name variable. Here, so we send -1 here, and then we send the pattern itself in the name. Okay, so the pattern has been generated using cyclic. Okay, it's a tool in Pwn tools to generate a pattern, 1024 bytes, and this is enough to cause a segmentation fault. After coding segmentation fault, we wait a bit, and that's how we calculate the offset. It's the same way you calculate the offset if you are debugging the application with Pwn tools. Okay, and then we return the offset as is. So now we execute Python 3 offset. Okay, so the offset is 104. Okay, which means we need 104 bytes, all right, to reach the return address or override the return address. Once learning the offset, we can now go ahead and create the exploitation code. Remember, in buffer overflows, the rule is the same, guys. Your payload, or of course, don't forget that this is only applicable to binaries where the stack is executable with no protections. Okay, remember this. So let's go down. So that's how it works. So the payload all the time consists of the padding, the shellcode, and the stack address. The stack address can be, it's always the beginning of the input. So this one is not EIP, so we're gonna have to correct this to stack address. All right, so the padding is calculated. That's the formula of the padding all the time. So we have the buffer size. Okay, the buffer size all the time, it is the offset. So the offset minus the length of the shellcode multiplied by the pattern. It could be A's, it could be B's, it could be C's, whatever you want. That's the padding. That's the first thing, or the knob. We use the knob to make sure that to make the program slide all the way to the shellcode execution. So we create the knob, and then we create the shellcode. The shellcode can be created using multiple methods. You can use the ASM shellcraft, which is what we will use in this scenario, but we're going to make it alphanumeric. And then we have the stack address. The stack address is always the beginning of the input. Remember this. So remember that stack address should be found during the exploitation phase, but in this scenario it is leaked in the code. Remember that. So if you go back and go here, remember that the stack address was leaked here. So we have the original stack address, but we want to make sure that the stack address points to the beginning of the input. So that's why, remember that the input is taken into the local 68, which happens to be the name. Okay, so it is 96 in bytes. So when we enter 96 bytes, the input, or the input shifts the stack address 96 bytes in the stack. So we have to extract 96 bytes from the stack address, the current one, to make sure that we are at the stack pointer, not the base pointer, meaning at the beginning of the input. So it starts with 96. Of course, we're going to enter 104 to reach the return address, but we have to be at the very start of the 96 bytes. That's why we have the stack, and we actually subtract it from 96. So let's go over the exploit code, nano exploit. First, we import Pwn tools, remember that, and then we define two functions, the get process and the main. The get process is the function responsible for executing the process, and of course we're gonna have to pass the IP address on the port as an argument, and they are split by column because that's the required formula here to connect. Alright, now let's go to the main function. Remember that in exploit code, guys, we need to mimic the user input process to be able to perform the exploitation and hit the binary with the segmentation fault. So we have first, as you can see, send line to send yes, and then we have, as you can see, remember that the stack address is leaked in the code, so you're gonna have to take it using receive until, and then we perform the necessary decode on the stack address using the decode function, and 16 bytes, we define 16 bytes, and we store the result in stack leak. Here we log the information to the output, and then we have the shellcode. This shellcode can be generated using ASM, but remember that it has to be alphanumeric. This function. So here we can find alphanumeric shellcode that executes sh, bin sh. Scroll down and you should find it somewhere here. Yeah, this is it. Alternatively, guys, if you don't want to rely on online tools, you can use MSF Venom all the time to generate an alphanumeric shell or alphanumeric payload. So we can use the following command: msf venom or sudo msf venom, okay, -f python -p. We are exploiting Linux, so Linux x64 because the binary is 64 byte, exec --platform Linux, and then the command will be cmd equal bin sh. Let's see. Okay. So what you can do here, you can copy that and go back to the code. Where is my code? Here. So scroll down. And you can say here paste. Let's go ahead and formulate this. So buff is the shellcode. You can rename the buff to whatever variable you want. Alright, and finally, remember to use alphanumeric, right, to make the shellcode alphanumeric. So here, buf equal alphanumeric buf, and then you take the variable and use it here instead of shellcode. That's an alternative method, guys, if you don't want to use online tools to create the shellcode. So we're gonna have to make a comment here. Okay, that's the shellcode. Next, we send the email as expected. So here the email, I used parts of the shellcode. The first 8 bytes from here will be sent to as an email, and then the next 8 bytes between index 8 and index 16 from the shellcode will be sent at an age, and then we send -1 to the length of the name, and lastly here, guys, we need to send the payload. So that's the final form of the payload. The shellcode, we have it. The padding, let's calculate the padding. I showed you guys in the notes. So we have the pattern of C's, and then we subtract the offset we found from the length of the shellcode, and then we have the stack address. The stack address was first acquired by decoding the address, the binary leaked in the input, right? But don't forget, we have to adapt the stack address to the current scenario. Remember that we have 96 of input to the name variable. So we want the stack address to be or to shift to the beginning of these 96 inputs. So we're gonna subtract the leaked stack address from 96. This way we point to the beginning of the input. Pointing from the beginning of the input, we have 104 of bytes. We can simply, guys, slide all the way to the return address. We send the payload here to the name variable, and we suppose that we will receive interactive shell. So we execute this, and we're gonna have to provide the IP and the port. We have an interactive shell, ls, and as you can see, guys, we have the flag, cat flag. So that's the flag of this level. So that was it, guys. I hope you enjoyed the video. And remember, if you want to get access to these notes, you can subscribe to the channel membership. Thank you for watching, and I will see you later.